quick history of biological and chemical warfare as it will relate to equilibrium. Generally, a history of people being evil. What we have here that we're looking at is Greek fire. So Greek fire essentially is an oil mixture, as we know, it's quite flammable. Think back to the potato chip that we did in class that we burned. So we have a large oil mixture here. The oil mixture is pressurized, mixed with saltpeter, which is potassium nitrate. Because the oxygen is a good oxidizer, it burns well. And when it's pressurized, you end up having an ancient flamethrower. So in ship battles, normally ships will go alongside each other to try and ram each other. There's a period of time, though, where this brass nozzle was affixed to the front of the ship, and as the ship got close to the other wooden ship, it would become a flamethrower and destroy or incinerate the other ship. People would fall into the water and things like that. So that was one of the first ways that people started using chemistry to hurt each other. In the 1300s, you had the bubonic plague or the Black Plague, and in different sieges, corpses that were infested with the plague would be catapulted over the city walls as the vector, I guess in both senses of the word, into the city. People would touch the body, that disease would get everywhere. It'd get into the fleas and the rats, and that would be carried throughout the city, and the whole city then would succumb to the plague.
Today, David Kirk is 55. He's planning a birthday he'll never forget.
It's quite unique. It's like one of those weird dreams, and it's speeded up very much. What's overcome with the speed?
In the 17th, 18th century, you had issues with Europeans donating tuberculosis-infected blankets to First Nations people. Now, what's interesting about this is that it was very well known, but then recently people were looking for documentation, and the documentation is a little bit harder to find for that. So there's been some skepticism whether this has occurred. Unfortunately, we do know that groups that go to another country and try and take over and dominate will do a whole list of horrendous things, and people definitely have that unfriendly side to them, we'll say. And we see this even more recently. A couple of years back, there was a spate of attacks where people were sending anthrax to their senators in the states, and buildings were cleared out because of that. And again, anthrax is another biological weapon. It's bacteria that's found in the soil on farms. It's available that way. It doesn't cost a lot to set up and grow, so people tend to, again, have that bend in towards biological weapons, tend to find these types of things and send them around. Now, all that being said, people have done things much worse on a much larger scale. That's what we're looking at today. Of course, as troublesome as individual people are and small groups of people are when they try and hurt others, it gets worse when you have a war situation. So here we have a guy called Fritz Haber, and Fritz Haber was a German scientist, and in the First World War, what he wanted to do was help his country at any cost possible. So he really worked hard to explore the role of biological and especially chemical weapons. Now, chemical weapons were an issue because he had access to the chlorine gas supplies at BASF, which is a chemical supplier. And using these chlorine gas containers, he was able to start seeing the effects on people and animals. He accidentally poisoned himself, he poisoned a few other people, he poisoned some horses, and eventually it was ready for an attack. So a whole series of these 5-foot tall containers weighing almost 200 pounds each were lined up along the German trenches. And the idea was that when the wind was blowing in a favorable direction, the tanks would be opened and the green gas would flow from the German positions to the Allied positions. And when this happened, Allied forces were covered with a huge amount of chlorine gas. It caused lesions in any mucous membrane. People were coughing up a lot of blood, parts of lungs, and other things like that. You might remember from Great 10 history, this is what happened when people end up taking their handkerchiefs, urinating on them and breathing through that, because the interaction between the urine and the chlorine gas created a precipitate and protected their lungs from damage. As well, we had Germans that were sending over shells of sneezing powder. The whole idea was that the sneezing powder would cause everyone to sneeze so badly they couldn't operate the rifles, and they would sneeze themselves out of capacity to fight. They tried tear gas, but it froze. The British troops tried poisonous gas against the Germans, but the wind changed directions and killed their own men instead. Now, this kind of people started realizing that biological weapons and chemical weapons have limitation, and the real way to get things done is to blow stuff up. So this led to a huge chemical need for nitrogen-based compounds. At this point in time, the biggest source of nitrogen-based compounds were deposits of penguin guano in South America. Germany was cut off in the Atlantic from reaching Chile, where this penguin guano was. Consequently, they had no way to access the nitrogen reserves, and therefore no way to blow things up. So Germany needed a way to obtain nitrogen for fertilizer and explosives. The textbook does a good job of talking about the fertilizer side of it. Reality was they needed a way to blow things up. And without having a navy to go and get it, or much of a shipping empire, because the British Empire would just take over the ship as it was coming back and steal all the guano, they needed another way to do this. So we have a problem, we need nitrogen. We have a scientist who likes to essentially hurt people named Fritz Haber. So he wanted to solve this problem with chemistry, and he started working on it. And that's what the video talks about.
Fritz Haber and Karl Bosch, the synthetic ammonia process. Nitrogen makes up nearly 80% of the air we breathe. High-energy electrical discharges make it react with oxygen and water to form dilute nitric acid. In the soil, this in turn produces the nitrates that are so important for plant nutrition. But on its own, this natural source of nitrogen is not enough to compensate for the impoverishment of the soil caused by intensive farming. As early as the mid-19th century, German chemist Justus Liebig stressed the need to replace the nutrients removed from arable soil in order to maintain or indeed increase its productivity. At first, Liebig confined his studies to minerals like calcium, potassium and iron, but later he also recognized the importance of fertilization with nitrogen. The saltpeter deposits in Chile offered an excellent opportunity for meeting the demand for salts containing nitrogen. As a component of gunpowder and explosives, saltpeter was also the reason for the war which broke out in 1879 between Peru and Bolivia on the one side and Chile on the other. With the backing of Britain, Chile emerged victorious, and Europe's supplies of saltpeter were assured. But it was clear that Chile's limited deposits would soon be exhausted, and that a shortage of nitrogen fertilizer would have disastrous consequences. Around the turn of the century, with the world population increasing at a tremendous rate, it was obvious that food would soon be in short supply. In 1898, British chemist William Crookes predicted that the next 20 to 30 years would be marked by famine, unless some way could be found of manufacturing nitrogen fertilizers artificially. Binding atmospheric nitrogen, Crookes declared, is one of the great discoveries awaiting the genius of chemists. By binding atmospheric nitrogen, Crookes meant converting the chemically inert nitrogen contained in air into a form that plants could utilize. Initial attempts focused on simulating thunderstorms. In 1902, Norwegian chemists Christian Berkeland and Samuel Eide succeeded in producing nitrogen oxide from nitrogen and oxygen with the help of electrical discharges, but the method required large amounts of energy. With its wealth of hydroelectric power, Norway offered ideal conditions for the further development of this method. But although the German concern BASF was part owner of a Norwegian experimental plant, the search continued in Germany, which has few sources of hydroelectric power, for alternative methods. In 1903, Carl Bosch, a chemist with BASF, began experimenting along these lines. He was helped later by Alvin Mittag. But the method they developed yielded such small amounts of ammonia that in 1908 the series of experiments was abandoned. In 1903, Fritz Haber also began to examine the problem of fixing nitrogen. He explored the possibility of manufacturing ammonia directly from nitrogen and hydrogen. One molecule of nitrogen and 3 molecules of hydrogen react to form 2 molecules of ammonia, NH3. Very high temperatures are needed to split the nitrogen molecule, which is chemically stable. But at excessively high temperatures, ammonia molecules that have already formed break down again into their basic components. So, as the temperature rises, the concentration of ammonia diminishes again. Walter Nernst suggested inducing the reaction under high pressure in order to increase the yield of ammonia. Haber took up this suggestion and made nitrogen and hydrogen react under pressure. To enable the chemical conversion to take place quickly enough at moderate temperatures too, Haber used a catalyst. After removing the ammonia that had formed, he passed the nitrogen and hydrogen gases over the catalyst time and again. The catalyst, which was not consumed during the reaction, permitted high enough reaction speeds even at moderate temperatures. Haber obtained good results with osmium, a rare and expensive metal. At first, BASF rejected Haber's findings, claiming that such extreme reaction conditions were technically not controllable. But Carl Bosch was able to convince top management at BASF and obtain their approval for the further development of the process. Haber then developed laboratory equipment which enabled him to bring the gases together at high pressure and at high temperature. The compressed reaction gases, hydrogen and nitrogen, were passed over the heated catalyst in a high-pressure cylinder. The gaseous reaction product ammonia was then liquefied. Thus, on July 2, 1909, continuous synthesis enabled the production of no less than 80 grams of ammonia per hour. Bosch was now given all the authorization he needed to develop the method to an industrial scale as quickly as possible. Bosch and Mittag began the search for a cheaper catalyst than osmium. After some 20,000 tests, they found the optimum catalyst, a compound consisting of iron and small quantities of alumina and potassium. But there was still another problem to be solved. Unlike the experimental converters, large converters could not withstand the high pressure. They shattered after only 80 hours. When Bosch examined the fractured tubes more closely, he discovered that the carbon contained in the steel had been eliminated under the influence of the hot hydrogen. A brittle alloy had formed which could no longer withstand the great pressure. Bosch came up with a brilliant answer to the problem. He used mild steel, which, since it contains little carbon, was no longer affected by the hot hydrogen. Since this tube was not really suitable for high pressures, he surrounded it with a casing of conventional steel. Now there was nothing to prevent application of the Haber-Bosch method on an industrial scale. In September 1913, the world's first ammonia plant entered operation in Oppau in Germany. Each high-pressure autoclave produced more than 3 tons of ammonia a day. The factory was a technical marvel. For the first time, the architecture of a factory had been adapted to a chemical process. Instead of the customary brick buildings, the plant was characterized by steel frame structures. Bridging roads on the site were supports for pipes, most of which transported gaseous and liquid substances from one stage of production to the next. Inside the factory, steam was passed over red-hot coals to produce the large quantities of hydrogen that were needed. Huge compressors condensed the reaction gases to the required high pressure. The actual heart of the plant, the high-pressure autoclave, the ammonia formed in it was discharged into the storage container. On August 1st, 1914, the First World War broke out. It soon became clear that Germany did not have a guaranteed supply of saltpeter, the basic material for making explosives. Bosch made his saltpeter promise. He told the country's military leaders in Berlin that he could come up with a method of manufacturing saltpeter in large quantities from ammonia. And at Christmas time in 1914, a hastily erected plant began producing saltpeter. Without the Haber-Bosch method, Germany's ammunition supplies would have run out after only a few months. So, ironically, the carnage of the First World War, which lasted for 4 long years, was only made possible through the large-scale synthesis of ammonia. In addition to this, Haber made a direct contribution to the conduct of the war. Always fiercely patriotic and committed to a German victory, Haber played a leading part in the development of poison gas as a weapon. He thus added yet another horrifying aspect to the war. The first poison gas operations were conducted personally by Fritz Haber himself. Despite this, in 1918 Fritz Haber received the Nobel Prize for developing a method of synthesizing ammonia. 2 years later, the Nobel Prize went to Walter Nernst, who had worked out the theoretical principles behind the method. It wasn't until 1931 that Carl Bosch received his Nobel Prize. After the Second World War, the demand for ammonia grew. The increase in the production of nitrogen fertilizers meant that plants had to be constantly extended and modernized. Ammonia became an important substance for the emerging chemical industry. The new plastics industry in particular needed basic materials that were derived from ammonia. In addition, experience obtained from synthesizing ammonia was applied to other high-pressure techniques. But the Haber-Bosch method itself has changed very little. The catalyst has been modified slightly, but the vast dimensions of these plants have remained the same. The core tube alone, seen here being inserted into the steel casing, weighs several tons. The completed high-pressure plant, which has an output of over 1,000 tons of ammonia a day. Today, world output stands at well over 100 million tons of ammonia a year. The manufacture of fertilizers still accounts for over 80% of this volume. The synthesis of ammonia on an industrial scale was undoubtedly a pioneering achievement, one which enabled mankind to utilize atmospheric nitrogen in order to solve its food problems. Commercial fertilizer enables even less fertile soil to be farmed economically. But high-pressure synthesis of ammonia consumes a great deal of energy. That's why much of the energy from the Aswan Dam, which was built in the 1960s, is used for producing commercial fertilizer. And man-made fertilizers are only needed in such huge quantities because damming of the Nile meant that the river stopped flooding the fields alongside it every year and covering them with nutrient-rich silt. The 80 million tons of nitrogen fertilizer that are manufactured each year result in an increased grain yield of 1 billion tons. Roughly the same quantity of nitrogen is fed into the soil worldwide via soil bacteria and through electrical discharges in the atmosphere. The specific use of nitrogen fertilizers not only increases crop yields, it also has a positive influence on life in the soil through the increased formation of humus. Excessive fertilization, however, has a negative effect on the environment. The scientific prerequisites have been created for applying commercial fertilizers in a more eco-friendly way. Sensible fertilization will be necessary in future too, in order to provide the world's constantly increasing population with a supply of food.
So, a little bit about Fritz Haber. A couple things to know about him. First, he was fiercely patriotic. He would do whatever he could to support Germany's war effort and whatever he could to make his country the best. Now, being patriotic is a good quality. There's a point there where it goes a little bit fanatical, and he was definitely in that spectrum. Now, what we have is we have a guy, Fritz Haber, who married another lady who was a chemist. Both of them had different views on chemistry. His view, as you could see, was to use chemistry to promote his country, to kill people in war, and make his country better. Whatever better is from his perspective. Her view is different. Her view was that chemistry can be used to help people, to feed the poor, to improve crop yield. So they had very different views on this. And this really came to a head in their relationship when he would spend a whole lot of time on the front lines of the First World War, personally supervising gas attacks. This was an issue because his wife had a huge problem with what he was doing and how he was spending his life, to the point where one day she went outside in the garden with a gun and shot herself. Her son, who was 12 at the time, ended up having to deal with a lot of the issues. Word was sent to Fritz Haber about, your wife has passed away, you need to come back. His response was, no, she's already dead, my son's 12, he can take care of that. So he left his 12-year-old son to take care of the arrangements of burying his mother. So it gives you a bit of insight into kind of his mindset and his focus and other qualities about him, which might make him less than a desirable person to be close to. Either way, what he did come up with, though, was impressive, even if that was the only aspect of his life that was successful, perhaps. Said the issue that Germany had was they were cut off from the guano supplies in South America. This means they had no way to access a supply of nitrogen that could be used for any type of warfare purpose. Remember, nitrogen as we have it in the air is diatomic nitrogen. The triple bond is very strong. It's almost impossible to break that apart. If you can get it react with hydrogen, you'll make ammonia and also produce energy in the process. Now, the formation of ammonia is an exothermic process. That means that if you add temperature to this equilibrium, you're increasing this side of the teeter-totter. By adding anything as a product, it shifts towards reactants. So the increase of energy does not make the production of ammonia increase. In fact, adding energy to this equilibrium will decrease your yield. First reason why it's difficult. Second aspect here, we have a 4:2 pressure ratio. There are more moles here, fewer moles on this side. Increasing pressure will cause the reaction to move to completion, which is good. So naturally, by increasing pressure, we can get more product. That makes sense. We've seen that with Le Chatelier's principle. We run into a problem though. The most common way to increase pressure is by increasing temperature. Think back to the gas laws from grade 11. PV equals nRT, P1 V1 over T1 equals P2 V2 over T2. Pressure, temperature, and volume are all very tightly connected. This means that we need something else to make it happen. We need a catalyst. In the video, you saw I think they tried about 10,000 catalysts, I think it says. A huge number of catalysts were needed to figure out the best way to make this happen. They eventually found out that iron 3 oxide was the best way to make this reaction go to completion. At a pressure of 200 times atmospheric pressure, yield is about 15%. That means that if this was drawn as an arrow, this side, the reactant side, are heavily favored. 85% of your system at equilibrium is on the reactant side. If you're drawing graphs here, these values are huge. This is a very small value over here. So there's a few things we know. First of all, we know we're only producing ammonia at a 15% yield. Although this is low, if we remove some of that ammonia, it means equilibrium will be disrupted, and we can have our reactants becoming products that will continually generate ammonia as we continually draw off some of the ammonia, which makes this into a process. So initially, we're going to start here with nitrogen and hydrogen gas. It's going to be compressed to the 200 atmospheres of pressure, again, so high that beyond what we can fathom, 200 times what you're feeling right now. It's going to be put into a chamber with a catalyst at 400 degrees Celsius in 200 atmospheres. The textbook has a very good graph of yield at different temperatures and pressures. Once this happens, the material is moved to a condenser. The condenser has a change in temperature, and we have ammonia condensing before nitrogen and hydrogen do. There's stronger intermolecular forces than ammonia. Those molecules are attracted to each other. They have a different condensation point. Consequently, you have unreacted nitrogen and hydrogen, which are recompressed and sent back into the reaction chamber. So what we have here is a way to draw off our ammonia essentially as it's formed through this condenser that leaves the top of the reactor, and you're able to continually produce ammonia. Now, 15% isn't very high. However, if you're continually removing it, you have a continual way to generate ammonia. And by scaling up the factories to some massive size, that 15% becomes quite a significant quantity. Your task now is to generate a mechanism. A couple things we're going to come up with. First, we're going to recognize that this is a heterogeneous catalyst we need. We have gases attaching to a metal surface. We have nitrogen being adsorbed and splitting, which is the rate limiting step. This would also now allow you to write a rate law for this equation. Hydrogen absorbs and splits as well onto this catalyst. Eventually they find each other and make ammonia. So think back to what we did in chapter 6. Take a few minutes and sketch out a quick mechanism. If you're not sure if it's right, ask someone else, or you can email it to me, or you can post it in Google Classroom and we can talk about it there. All right?